So the disease that I focused on for this piece of work is malaria. I recognize that there are some people in the audience who know a lot about malaria, but just in case some people don't, malaria is a life-threatening disease, and it's spread by mosquitoes, which we deal with in this methodology with a delay. So a mosquito has to bite a person to get infected, do some biological processes. I'm an engineer, not a biologist. So do some biological processes, and then they can then bite another person. And in the model, I'll show you how this is captured in the maths, but we just treat it as a delay. We don't individually, or we don't consider a mosquito model in this framework. Symptoms can be mild or life-threatening, and it causes the most harm in children under 5, pregnant women, travellers, and people who are at high risk, people with HIV or AIDS. So the context that we're looking at is near elimination. So here's a picture on the screen of the countries which are currently, I would say currently, I think this is maybe a bit old, but is infected or has endemic malaria. And then the WHO and the countries are trying to work at eliminating malaria. So elimination is the removal of transmission within a country, like locally acquired malaria, and then eradication would be like no malaria coming into the country. But it's quite tricky for individual countries to kind of control importations, and unless you do things like screening. But this work's focusing on elimination, so looking at countries which have little transmission locally within the country, and it's a large scale problem with in 2020 627,000 deaths worldwide. So the research question that I was trying to look at with this work, which is actually a few years old now, is looking at what proportion of the cases within a country are acquired from local transmission. So they don't travel anywhere, they're just in the country and they get infected, versus those who get the disease elsewhere and bring it back to the country with them, or imported malaria cases. Trying to work out what's driving transmission. If it's within country transmission, person to person, then this probably isn't a country that's close to eliminating the disease. And if it's being driven by importation, these are the countries which are close to elimination. And we want to do this using incidence data. So people reporting to a clinic, and mostly these data is people reporting to a clinic saying that they have symptoms and then getting a test to say that they have malaria. Traditionally, you kind of work out if a case is imported or not based on travel history. So they ask the person when they come in with symptoms, have you traveled anywhere in the past 3 weeks? And then they say yes or no. This isn't super accurate because the person may have traveled and still got the disease within the country. They might not want to disclose the fact that they traveled, especially this happened quite a bit in COVID, or if they're kind of moving for work, they might not consider kind of their travel. You can do this with genetic. You can sequence the malaria, but this is expensive, so not very rarely done. Although there is new technology now, which is making it cheaper. But people still are doing this kind of separation using travel history. So we're looking at, can we do this can we answer the same question using modelling? Can we work out what proportion of cases in the line list are imported versus locally acquired? And we decided we wanted to use this type of process called a Hawkes process, which is so self-exciting point process. So for those of you who are kind of have math degrees, you might be familiar with a Poisson process. But if you're not, you can think of a Poisson process as in like arrival times of buses. So kind of you expect one bus every 20 minutes, but in reality, they all come at the same time from my experience living in London. Actually, it's worse in Bristol. But this idea that you have a time, so looking at this as a temporal process, you have a time between, an expected time between your events, but it's a stochastic process, so it might not be exactly 20 minutes. So this is like the importations. We model this with a Poisson process. But then the Hawkes process is this idea of self-exciting. So if you have one infection in an area, that's likely to trigger more infections. So we have the second term in the equation, which allows this infection. So if you have one event, it's more likely to trigger other events, whereas a Poisson process is just a fixed, there's a fixed time between your events. So in maths, we write this. So we think of the intensity of infection. So this is like the force of infection, the amount of infectiousness that there is in your population. And this is equal to some background contribution to intensity, or like a Poisson process, plus this self-exciting term, which is the second term in the equation. And we can think of the background term, this mu of t, to be your imported malaria cases. So these are the people who come into your kind of area of interest, whether this is a country or a region, with the disease, and they aren't infected by anyone else on your line list. And then the second term, which is the contribution to the intensity from direct transmission within the country. So this is somebody getting affected by somebody who lives in that community. And what we want to do is we want to work out what proportion of infections are coming from the mu versus what proportion are coming from this summation of G of T minus Ti. And these can be kind of parameterized quite flexibly. There's quite a lot of papers now, especially during COVID, for various different formulations. But what we consider is it's quite simple. For those of you who are kind of familiar with renewal-based methods, this is like the methods that go behind EpiEstim and EpiNow too. This kind of renewal equation. Quite often it doesn't have this importations, although I'm sure Sam can tell me exactly what's in EpiNow too, whether you have this kind of idea of this background, this exogenous imported term. But we have an integral, but in the Hawkes process, we have the summation, and this term here, this f of t minus tau times your serial interval. This is represented by your kernel. With a Hawkes process, you need individual event times, so each infection needs to be unique. Whereas in the renewal process, you can have aggregated, you have the number of infections per time. But that's kind of the reason we didn't use Hawkes processes for COVID, was that suddenly we had all these infections and we didn't have unique event times for any of them. So like I said, we can choose how we parameterize this second term, and we call this kind of a kernel. It explains how a person's infectious profile changes through time, a little bit like the serial interval. And like I said, for malaria, there is this idea that there's a period of time where the mosquito has to be involved. A mosquito has to bite one person, become infectious themselves, and bite a second person. So we reflect this with this kind of flat term here, or this delay, or this delta. And then on the left plot, this is saying your infectious decays exponentially, and then we impose a Rally kernel on the right. Traditionally, with Hawkes processes, they use an exponential kernel, and this is saying that the next event is most likely to occur at the point of the first event, which works quite well for earthquake modeling or financial modeling. But we didn't think that it was necessarily such a great assumption to make for infectious disease modeling, where you have this kind of potentially ramp up of infectiousness. The peak in your profile isn't at the point that you're infected. And then we kind of have these two parameters, this alpha parameter and this delta parameter in both. Alpha is like a magnitude, how like that controls the peak. So if you have a high alpha, there's a strong peak in your kernel. And then this delta, it tells you how quickly the infectious profile decays. So if you have a treatment for a disease, delta is likely to be shorter than if there is no treatment. So then we look at how you can parameterize your background term. Again, you can choose kind of anything for this. And if I did it again, this is not what I would have chosen. But we're saying we wanted some flexibility. The idea was that these countries are trying to get close to eliminating the disease. Maybe the countries that are close to them are also trying to eliminate the disease. So we wanted some way for our background intensity to decrease through time. So these parameters could be negative. And we wanted some kind of sinusoidal shape in our model, because malaria is a very seasonal disease. The number of peaks and when the peaks happen depends on the country. But we wanted this idea that you could reflect the rainy seasons where malaria is most likely to happen. So we parameterized this model like this. What's nice is about Hawkes processes is it's really easy to calculate a parameter that's close. I think about the reproduction number. So you get your branching factor. Can calculate this. This is n star, and it's the integral of your kernel. And this is analogous to your case reproduction number. So the number of people that a case will go on to infect. And this, for our examples, is alpha over delta, which is quite nice. This audience probably is very familiar with what a line list looks like, but the idea is that you have in each individual, you have a line in your data, which is what's called a line list, and then you have certain information about your people. So maybe the date that they first get symptoms, the date that they get a test, maybe the date they get hospitalized, and some demographic data. If you were to do this kind of the best as possible, you'd be wanting to use date of infection, because we're looking at the time between infections, or that's the event that the Hawkes process is modeling. But it's quite typical of this type of modeling is that you don't necessarily know when a person was infected. So we've done this work using date of symptom onset. And if the date of symptom onset isn't available, we have done some crude interpolation based on the mean time between symptom onset and test. This can be obviously improved. Didn't find it had too much of an impact. And the kind of data sets that I've been fitting to are of the order of about 1,000 people. There's no hard and fast rule, just that the fitting is relatively quick. But if you want to simulate these trajectories to do any forecasting or to see how, like, what your fits look like in reality, gets a bit computationally expensive. But that's an area of research that I'm interested in. how to make these more efficient. So you can fit your model and make parameter inference for Hawkes processes in 3 different ways. So there's maximum likelihood, which is kind of the traditional first frequentist method that you kind of learn in a stats degree. Then expectation maximization, and then also Bayesian inference. So I'm just going to take you through how you would do these 3 types of inference. So with Hawkes processes, you get this this parameter. You can calculate your log likelihood based on your data. You can say how likely are these parameters to have caused an outbreak of this size with events at these times. So mathematically, it's very easy to derive your log likelihood. And then the idea is that we want to minimize the negative log likelihood. So we want to choose the parameters which cause negative log likelihood to be as small as possible. And you can use kind of inbuilt algorithms in R or Python to do this optimization. The problem is that sometimes the parameter space is quite complex and flat in some areas. So we did find that if we were trying to fit all of the parameters, we ended up in kind of a flat region of our optimization surface. And in the end, decided to use values from literature for the delay between a person becoming the time for the mosquito processes, because when we tried to fit them, we were ending up with some very strange, not biologically possible results. So here is kind of some fits that we got. I think this is from data from China. So we fixed this delay to be 12.5 days, and then we fitted the kernel and this shape. So with the data in China, there's a very good healthcare options available and treatment regime. So this time of the infectious profile is shorter than perhaps you might expect from other countries. We also note that this is the background term here on the right, and it's very strongly decreasing, suggesting that this country is getting very close to eliminating both local transmission and also background transmission. We fit this to not the whole of China. This is just one province. I think it's Yunnan province. A problem with this method is that it's quite tricky to get any measure of uncertainty. So you use the maximum likelihood methods and you get kind of a central estimate for your parameters. From reading the literature and speaking to other people kind of working in this field, some people point blank refuse to give uncertainty estimates, which kind of was surprising. But you can do it through simulation. So you can simulate a new data set and then you can refit to that. And then you can use bootstrapping to calculate confidence intervals for your fitted parameters, which we have done here. And if you're interested, kind of there's a URL to a paper that talks about that this algorithm came from.
But can I just ask, do you mean like in the Hawkes process literature, they don't like uncertainty, or?
Yeah. In Hawkes process, like with maximum likelihood. Like I reviewed a paper and I tried to push back and said, can you give some uncertainty estimates? And the person said no. I was like, there are ways, the ways you can do it. You can also do something with the Hessian from your optimization, but when I tried to get that working, I was getting some very strange results. I think because the optimization is tricky, and like Optim is not necessarily a very great optimizer, and trying to get some of the other ones working reliably and across different compute systems is really tricky. So I don't my preference now is not to use this method. I've switched to a Bayesian approach. Or perhaps expectation maximization. The idea here is it's like a two-step process where you calculate a latent variable, which is the terms on the left. I just switched the notation here. Divided through by delta. So you end up with this omega parameter here. Because this is the way that this lot of slides were written. But the idea is that you calculate the probability that each infection was caused by each other infection in your data set. So this is this Pij. And then you can also calculate this PII, which is the probability that each infection is calculated by each other infection. I is contributed from the background, sorry. So this is like the probability, the top one is the probability that it comes from your person-to-person transmission kernel, and then this is the probability that your infection came from the background. And then you can use these probabilities to incrementally update your estimations of your parameters, and you can iterate between these so that you get convergence, so that you estimate, kind of, you have one set of parameters, you calculate your PIJs, then you use them to update, and then this mu k plus 1 is within some small tolerance of mu, and then you can say that your method has converged. What's really nice about this method is that you end up with these matrices for the probability that each case in your line list was infected by each other case in your line list, and from the background. And I did some work here trying to recreate transmission chains, so working out who infected who in your data set, or well, that is really tricky with temporal only data, because you end up with lots of infections all occurring at the same time with a small probability that they were caused by each other infection. But we did look at this a little bit to say which cases are likely to have come from the background infection. So those would be like your importations, and for some other diseases other than malaria, like maybe Ebola, you wouldn't expect very many imported events. So this is kind of thinking that this is an idea of missingness. If your case is, if the Hawkes process is telling you that this case came from an importation, it means that it was infected by somebody who wasn't in your line list, which means it's probably infected by somebody who hasn't reported that they had the disease. But yeah, this is kind of very much still ongoing research, and what I'd like to be able to do with these Hawkes processes, and I'll get on to this more in the end. But this is what I like about this method, is you end up with your these matrices, like your latent parameters are really actually useful information. But again, calculating uncertainty is quite tricky in these methods. This is kind of what you end up with temporal only data. You end up with, like, yeah, it's very easy for the second case to say that one definitely came from the first case, but as soon as you have case 5, it could have been affected by all the previous cases. So you don't really get identifiability in your transmission chain with only time data. If you want to calculate uncertainty in your parameters, the best, in my opinion, I would switch to using Bayesian inference. So we used a probabilistic programming language called Stan, which nicely allows you to code up your likelihood. So this is what we're doing in the first part on the left-hand side. We just calculated based on, so for some given parameters, so our parameters are mu, alpha, delta, for our events list, so that would be the times of infections. We can calculate this log likelihood, which is the same log likelihood as it used in the MLE, maximum likelihood expectation step. But as we run through this using MCMC Markov chain Monte Carlo, and Stan uses Hamilton Monte Carlo, it's possible to get a distribution for your parameter estimates. So here it's just a simple toy example. Set mu, so a background intensity, to be 1/2. And then we used an exponential kernel here rather than a Raleigh kernel. End up with the summation. So we set alpha to be 1 and delta to be 2. So you can see that we recover. So for mu, we have a central estimate of mu to be, I think it's slightly greater than 1/2. There's no, slightly greater than 1/2, but the distribution encompasses 1/2. Then alpha, the central estimate, is about 1. And then delta, our central estimate, is slightly over 2, but again, it encompasses it. I'm pretty sure that this was done by my student, Ethan. The more events that you have in your time series, the better estimation of your parameters you get, assuming that your parameters don't change. So this was fit to simulated data. So we simulated time series with these parameters. If you simulated a longer time series, these estimates get more certain. So you end up with shorter tails on your distribution, and they center better around your the parameters. But the idea is that with these Hawkes process methods, you can get a good understanding of uncertainty in your parameters. So as I alluded to, you can also simulate from these parameter distributions. And the idea of simulating is trying to work out, well, we used simulating to tease apart the contributions from background and the kernel terms, because you can simulate from just the background term, and you can simulate from the whole process. And one of these methods is called thinning. And the idea is here is kind of a little bit like rejection sampling. You choose, you simulate when you expect there to be, when the next event could happen. And then based on some probability, based on the amount of infectiousness, so like the summation of all the way through people, infectious profile they are, we then choose whether to keep that or not. So the first thing you do is calculate the upper bound of the Hawkes intensity. So this is like the maximum intensity that you have in your system, and then you sample an inter-arrival time, and then you choose to accept that time if the intensity. So if the intensity is close to the maximum intensity in your system, then it's likely that you'll accept that event. But if it's not, then you will reject that event. And this is first developed by someone called Agata. This is very tricky for the malaria simulation that the parameterization that we came up with, because of the sinusoidal shape of the background term and the fact that our background term decreases as well. So these kind of points are suggested, or kind of event times, and then the probability, then the intensity based on that event time. So if we remember that we first imposed some kind of delay, so you get the first point, and then there's some period of time where that person can't go on to infect anyone else. And then you get these shapes, but the pink time, this in the first plot, this pink dot is like the maximum time, the maximum intensity that you would expect based on purely the last event. But actually, because you have to consider that your background intensity is decreasing, you end up with your maximum, which is this black line, actually being slightly earlier. And then in the second example, you might think that your maximum intensity is at kind of day 11, but actually your maximum intensity is at day 22 because of this sinusoidal shape. So it was turns out to be very inefficient to use the thinning algorithm, because it's really dependent on knowing when your maximum infection time is. So you can use this other type of simulation called cluster-based, and this is when you take each parent and you sample or you simulate all of their children, and then you go to the child event and you simulate all the children from that, and then it doesn't matter that your background is doing crazy things. You first sample from your background, and then you know that you've captured all of the seasonality variables. So this is fit to some data in Yunnan province. So the plots look very similar, and this is because most of the cases in this Yunnan province in China were importations, which is the right plot, versus daily cases. So the red is the raw data, and then the black is, I think, 10,000 simulations, and the red line falls nicely within our black line. So this is kind of saying that our Hawkes process is capturing the behavior that we see. This purple line, I can't remember, it was a null model. I can't remember exactly what that model was, but basically the null model couldn't capture this behavior, but the Hawkes process could. The next thing we looked at was missingness in your data. So traditionally there's kind of, they're using very complete data. So it's like, when all the earthquakes have been. What happens, how robust is this method to when you have different amounts of missingness? So here are the different parameters in the model, the alpha, the delta, and the 3 parameters for the kernel. What happens, can we recapture our true parameter, which is the red line, when we reduce our data? And we find that because the majority of cases are coming from importations, the alpha and the delta, we can still capture the true parameter up until very low, very much messiness. Sam, it's already, well, it's 20 minutes. Do you want to do the question now, or?
I think if you've got more stuff that you think is interesting, it'd be great for you to keep talking. Yeah, I just wanted to point out that we're at 40 minutes, and also, is this missing at random, or is this?
So this is missing at random, but my student over the summer, not summer, last term, looked at missingness in terms of reporting. So missingness close to the, like, early on, so you have poor testing, and missingness close to the end because you haven't got all your data. Unfortunately, it was a short project, so we didn't get too much details. But it really depends what regime you're estimating. So here it estimates the background quite poorly, because if you have missingness in your data, it's saying that you have fewer importations, so it reduces the contribution from the background. If most of your cases are coming from your kernel, then you get sometimes it causes the alpha and the delta parameters not to fit well. So it's tricky to do this on real data, but missingness does have an impact. And then these are the kernel shapes, and this is importation. Oh, this is in Bhutan. So we did a second piece of work looking at Bhutan instead of China. And here, malaria, you have 2 different species. You have falciparum and vivax. The difference between these, well, there's lots of differences, but the main one that caused issues here is that with vivax, malaria, the parasites will lie dormant in your liver. And then it can be reactivated and you can get another case. But it's not caused by any other case in your line list. It's caused by the reactivation of the parasites. And we find that we get an okay fit for falciparum malaria, which is the left plot. But on the right plot, this green line is importations. And our model is saying these blue simulations are saying that we should be seeing more importations than we actually see. And I think this is because the labeled data that we don't fit to is accounting for the relapses, which we can't capture with a Hawkes process in the current parameterization. So here's kind of what the like a really old paper, it's the only one I could find, about trying to capture what happens with Vivax malaria. So you have this initial peak of infections. So this is like the weeks after recovery from a primary attack. So you get this one peak and then get a long time after, and then you can get this other peak, which the single, like the kernels that we were looking at earlier, just can't capture this. And I think this is why we don't get a good fit. So quickly, what's next? I really am interested in this idea of recreating transmission chains, but as I said, doesn't work with temporal only data. Just thinking about adding other data. So the obvious one to do is spatial data. And there's been a lot of work on Hawkes processes with a spatial kernel. So you could put like an exponential kernel here saying that a person who's close, you're likely to infect somebody who's close to you in space. But this got me thinking, that is this enough? Will this sufficiently enable me to recreate these transmission chains? And I don't think so. So I started looking at genetic information. But yeah, I'll finish there. And thanks to some students, Aisling and Ethan, who wrote some of the code and did the experiments. But I'll open the floor for questions.
Thanks. That was super, super interesting. So we still have just over 15 minutes for questions. And if we don't get to anything, there's a discussion thread that I posted in the chat that I imagine Ettie will be open to having a look at and responding to if anything comes up.
I'll just make yeah, does anyone have any questions?
Kelly.
Thanks, Ettie. That was super interesting, and you explained it very well, even the maths bit. So I appreciate that. I want to go back to near the beginning, you talked about needing unique event times. Could you explain that a bit better and also talk about the generalizability of these methods to look at other diseases that we're looking to eliminate, like say polio, for example?
So I'll start with the generalizability. It's very generalizable. You just give it, you just parameterize your Hawkes process. So you have the background term and the kernel term, and you can choose whatever shapes. If you can differentiate them, then you can have those shapes. What I'm really interested in is disease agnostic methods. So methods that you can kind of use for lots of different outbreaks. I've looked at Hawkes processes for Ebola. People have used them for COVID because this comes into your other part of the question about these unique event times. But the way it's parameterized at the moment, you're looking at inter-arrival times. So the time between events. So time between infections is more important than the actual time of infection. And if you knew that you had 5 infections all on the same day, you wouldn't know the time between them. And it's the time between them that kind of enables you to do the calculations. Because if you think about the expectation maximization setting, you want to calculate the probability that each infection was caused by each other infection. And if you didn't know when the infections happened, you wouldn't know those probabilities. It's probably like
is that kind of related to a censoring problem? So like if you had weekly data, for example, that would probably make this much harder, if not impossible.
Yeah, so we don't have unique event times for malaria. If it's a few numbers of cases, we jittered them. So we said, we know that these cases happened on this day. Well, we know these people reported these cases on this day. And then we said, randomly distributed the event times during the day. You can do weekly data, but you can assume that you can distribute it through the week. But I've done a little bit of experimentation to how you do your jittering, like if you assume it's uniformly distributed. I mean, with times of reporting, people aren't going to report in the middle of the day, in the middle of the night, probably. So you could kind of center them around the middle of the day or something like that. For infection profiles, which are in the order of kind of a week, the 24 hours doesn't seem to kind of impact the fit too much. It obviously could impact if you had a disease which you could transmit in a day, but I've not worked on loads of diseases. But if you could get infected and affect somebody the same day, then that could be problematic.
Got it.
And also if you get diseases where you can affect people before you show symptoms, that would be quite tricky. During COVID, people did come up with this idea, it's called binned hawks or aggregated hawks, where you can fit to aggregated data, so like weekly data, but as part of this, you are fitting a latent process, which is your unique event times. So people go back and infer the unique event times to then infer the parameters. But I've not tried any of those methods. I think they would be computationally very expensive and require good data, which I think with diseases you don't necessarily get.
Thank you. Sam, do you want to go or call on the next person? Oh, A. Taylor.
Hello. Thank you for your talk, Juliette. I am a postdoc and I work on genetic relatedness between malaria parasites and infections. And I just wondered if you knew how you might go about integrating genetic information.
I think it's hard. For me, the mosquito makes these things quite difficult. But I've got some collaborators who are collecting parasite genetic information, and I've seen this done for non-malarial diseases with like this idea of like a Hamming distance, or I think it's called a Hamming distance. So you get your SNP, which is your ACGTs, and then you look at how different those are between your two parasites, and then you can look at how closely related they are. It's difficult for me to think about how you parameterize this, because like the genetic component is like an output of this. It's these two infections happen, so they're related genetically. It's not like a causal thing, like in close in time and close in space you're likely to get infected. You can't be close genetically until the infection has happened, because as a result of the infection. So there's a type of Hawkes processes called marked Hawkes processes. Instead of adding a kernel term to the end, you add this mark to the start. So I was thinking maybe having some mark with a genetic component. But this is what I'm really interested in looking and thinking about more. I think there's now some data that's being collected that would mean that we would be able to start doing this work. But I started a new position and I have much less time for research, unfortunately. But if you have any ideas, I'd be really interested to kind of hear your
Maybe I'll follow up later.
yeah.
Thank you.
Sam, do you want to go ahead?
Sure. Yeah, I thought that was a really great talk. I thought you did a really good job at explaining really tricky stuff. I just had a clarifying question and then an actual question. So my clarifying question is, you said early on that we couldn't do this during COVID because we didn't have the right data. And I think maybe we couldn't do it because there was too big a scale rather than not the right data. Because what you're actually using, right, is individual level event times by date.
Yeah.
And then you're jittering it out to get like continuous time events, which you could have done in COVID.
Yeah,
But
we
the
tried.
problem is scale. Is that true?
We tried to do it. I think the problem at the start was it's infections. So we needed to
Yep.
know the time people were infected.
Yep.
You missed the majority of infections early on in COVID. You didn't know when somebody got infected. You just knew when they died, which is kind of, sorry, the reason we switched. For those of you who don't know, during COVID, I worked on a framework which we inferred infections based on deaths, and we fit to death data. It was unclear in a Hawkes process. We could have embedded the Hawkes process in the same framework, but we had so much underreporting, we wouldn't have all the true infections, and it became complicated to think about. People did fit the aggregated or the binned Hawkes to COVID data, and there are some references. If you post that question in the thread, I can find the papers for you. I just can't pull them up straight away.
That makes sense. My follow-up actual question is kind of you just answered, which is, have you thought about slapping this in the kind of like, delay, partial observation, framework, or some extension thereof? Because that seems like it'd be pretty interesting.
No, like I said, I have not really done anything. I have very little time for research. But I think these questions would be interesting. I guess to me, it's like, what's the benefit of a Hawkes process versus a renewal process?
Yeah, that's what I'm asking, really.
Yeah.
I'd like to know that. Like, should we all do this? Is this what we should do?
I would say for small outbreaks where the event times, Hawkes processes are very useful. For large outbreaks, if you're doing like binned Hawkes, why not use a renewal process? I don't like. It would be amazing if you could go from like an aggregated Hawkes process to recreate the transmission chains, but I just don't think there's going to be enough signal in the data. Especially as you have like one observation, like you have one realization of this Hawkes process that you see, which is right? You can simulate from it, which is like thinking if you were in alternative universes, how might this outbreak have played out? But I just, especially with time only, you're just not going to get enough information to make a Hawkes process useful, I think. Mostly the people who've done the aggregated Hawkes stuff with COVID weren't epidemiologists. They were coming at this from a perspective of, we can do these things, which you can do, but how useful is it? Yet to be determined. Or if anyone listens to this recording and has other thoughts, then I would be keen to hear.
Okay, I have another question. So Sam and I always like to ask what would you do differently? And you alluded to the fact that you would have used a different background term. So now that you finished, if you could do it over, what would you use?
So A sine X plus B sine X, it's not very identifiable. So you could use like this takes me back to my A-level maths day. I can't tell you off the top of my head, but you can get like sine 2 thetas, a parameterization like that, which allows you to get the shape, but you're not fitting like a constant term to the front of two parameters. You're fitting like a phase and a constant, which means that there's probably more, you can probably fit that that better.
But does it have the same shape? It's just
you can get
parameterized
them to
differently?
have the same shape, yeah. But you don't end up with like two parameters that you can like get the same thing. That's like you can get the same output from like your terms being very different because they're coupled, and that's really bad for optimization surfaces. I think I would also like to explore the missingness a lot more and more robustly, because we're doing simulated data, so you can kind of make assumptions on how you like, or what, like however you want to do the assumptions, you can do that. And I want to sort out Vivax. Doesn't match Vivax very well, but that one still is not clear to me at all how you would do that, because quite often people don't know they're relapsing, and maybe there's other people here who know more about malaria than me, but it's tricky. I don't think that relapse is very well understood, so then taking the biology and parameterizing it is tricky. Or the other thing is, there might have been misreporting of importations in Bhutan because it's a lot of people who travel for work. And so the malaria is driven by people coming from India to Bhutan for their work. And it's whether they declare that they've traveled because they may be illegally traveling and things like that. So yeah, I think it's the maths that doesn't capture it, but it could also be behavioral things.
Sam, do you have another question?
I do. I just wanted to get your perspective on this, which I think people might be familiar with. Have you come across HHH4 in the surveillance package, the endemic epidemic framework? Okay. Have you come across the importation functionality that Robin Thompson added to EpiEstim?
Vaguely, but I've not used it. I've spoken to Robin.
Yeah. Okay. So you probably just talked about cricket, but so basically it's like adding an import term on top of a renewal, but on like a count level, for like a renewal level count aggregated framework. And HHH4 is a frequentist version of that, where you can fit models to both those things rather than like passing in the imports. You can fit arbitrary terms. If you haven't used them, then this is going to be a difficult question to answer. But my question is that it sounds to me like it might be very related to a binned Hawkes process.
We take this offline. I have no idea.
Okay. Okay, fair enough. Because my follow-up question to this very hard to answer question was, okay, what is the benefit of using a Hawkes process over that? To which I think the answer is it's individual level probabilities. You can try and construct the transmission chains. You can use individual level data. Is that that's the big appeal? That's
my big takeaway from Hawkes processes. But so I don't really understand this binned approach. Why not switch framework? But maybe they're doing the same thing, and multiple things doing the same thing isn't bad. It's just they're just different.
Okay. It sounds like there's a good bit of work on the clarity of methods here. Unless anyone has a reference.
No, they've shown that Hawkes processes are like compartmental models, similarities to SI. Then Sam Batt's group are doing a lot about branching processes. So they looking at generating functions and how you would generate these things, which has links to both Hawkes processes and renewal processes. But I don't think anyone has directly compared the two. Hawkes processes. So this work I did before COVID was one of the early ways. It'd been used by I think that name is Kelly as a surname in Ebola. Not this Kelly. They'd done some work, and they'd done a non-parametric Hawkes process and used that for some Ebola work. There was one paper on, I think it was strep, that they'd done some modeling, and I had a really nice chat with the author of that paper because they reviewed this paper and wrote their name on it, and we had a chat. So yeah, that was interesting. But now there's a lot of work. There's a lot of people who've done some odd stuff with COVID. there's some good stuff with COVID. I guess a bit like all of COVID modeling. But it'd be interesting to see where people go with it now.
Yeah, awesome. Okay, well, thanks very much for that. We should probably wrap because everyone has to go to their next meeting. That was really good. That was really interesting. Next month we have Finlay Campbell from WHO, and I think it might be interesting because he's done quite a lot of work on count level modeling, looking at aggregate, looking at fitting to geospatial and genetic data, which is kind of where you'd like to go. So maybe there's some overlap there, but yeah, there's a question thread if anyone has any other questions we can get to, and I'll try and post some of the questions we had here, and I might look for some papers because I haven't come across bin talk processes before. Sounds very fun.
Yeah, I mean, I read the papers because I was really interested at like how do they do this, because there are some benefits, but then I was like, I'm interested in efficient methods.